Hello and welcome back to Multidimensional Integration, the video series where we talk about the Lebesgue integral in Rn. And in today's part 17, we continue our discussion about the LP spaces. More concretely, we will finally define the so-called L-infinity space. In short, this space is given by the essentially bounded functions. But before I give you the precise definition, I first want to thank all the nice people who support the channel on Steady, here on YouTube or via other means. And please don't forget, as a Steady or Patreon member, you can download the additional material for all the videos. And now without further ado, let's immediately start by looking at our original LP space. And as we have learned in part 16, these are the functions where the pth power is integrable. So in the case that p is equal to 1, we just talk about the Lebesgue integrable functions defined on Rn. However, we are also interested in the case that p is greater than 1, which means we consider all numbers in the interval from 1 to infinity. And now it turns out that one can nicely extend the whole theory such that we can also make sense to the case p is equal to infinity. So you could see it as a limit process where we increase this power more and more, but in the end, p is equal to infinity should not be read as a power anymore. Indeed, we will find that for L infinity, we don't need to work with an integral anymore. And as already mentioned, L infinity is given by the essentially bounded functions. And we will define this new term here with respect to the Lebesgue measure. So we will extend the common notion of bounded functions. So maybe let's first visualize a standard bounded function, which means we have a graph that does not go to infinity at any point. On the other hand, for an unbounded function, you can find values as large as you want. And now the essentially bounded functions will include all the bounded functions, but also some unbounded ones. So to see that, let's immediately write down the definition of L infinity. And as for the definition of the LP space, we just consider the measurable maps from Rn into C. More concretely here, C carries our standard Borel sigma algebra and Rn our Lebesgue sigma algebra. And then measurable just means that the pre-images of the Borel sets are Lebesgue measurable in Rn. Okay, so this is the standard as always, and now we want to know what essentially bounded means. Now, if we had a bounded function, we could just write down a bound capital C. So a positive real value that the function cannot exceed. And whenever I say something like that, obviously we just talk about the absolute value of f. This is the common way to deal with complex values, and also these graphs you should see as the graphs of the absolute value of f. So again, what we have here is that the value is bounded by c no matter what x is. Okay, so this is the ordinary definition of a bounded function. And now comes the extension that we don't care about what happens at a set with Lebesgue measure 0. So let's call this Lebesgue measurable set just A. And now we only need to satisfy our inequality outside of A. So this is the whole definition. This is what an essentially bounded function actually is. So it's not important how we can choose C and A, just the existence is needed. And in order to see that, let's immediately look at an example. So we need an example of a function defined on Rn, which is not bounded, but still essentially bounded. This is not hard to come up with if we just look at the one-dimensional case. Because there we could take the natural numbers as the exception points. So for example, we could say the value f of x is given by x itself if x is a natural number. And otherwise we just set it to 0. Hence the graph here is quite simple, we are always at 0 and we only have countable many exception points. However, the values at the exception points are not bounded at all. Nevertheless, we can satisfy the definition above by choosing a as the natural numbers. And then you also see any positive constant c will also work for this inequality. But as you might already guess, it would be really helpful to fix the smallest possible c from this definition. So in the example here, it would be c is equal to 0. In fact, going to the infimum of all possible c's there gives us the so-called L-infinity norm. And you might already know, it's not actually a norm yet, but almost. But before we go to the equivalence classes, as always, let's first define this infimum here. So we just consider the non-negative bounds we have called C before. Which means that the condition is exactly the same. We have to find a set with Lebesgue measure 0 such that this inequality is satisfied. So you see, this set A can definitely depend on the chosen constant C. In the example above, you can see that if we set C is equal to 2, then we could exclude 2 points from our set A. But obviously this is not really helpful, and the infimum will optimize for us such that we get the smallest possible C out. And in the example above, this one is clearly given by 0. And this already tells us that we don't have a norm here, because f is clearly not the 0 function. However, you can easily check that all the other norm properties are satisfied, so we just have to fix this one. And there you already know, this is not so hard, it works exactly the same as for the other LP spaces. And for the sake of completeness, I will also write down the definition of these equivalence classes again. More concretely, we just need an equivalence relation on our vector space L-infinity. And if we use a tilde for the equivalence relation, then this thing here denotes the set of equivalence classes. And there you know, this gives us our proper L-infinity space. So it's not a space of functions anymore, just a space of equivalence classes, but usually this is not a big problem. And now you should know that two functions f and g lie in the same equivalence class if their difference has an infinity norm of 0. Hence, the only points where they don't have the same value is a set with Lebesgue measure 0. So equivalently, we could just write that there is such a set A, such that outside of A, f and g are the same function. So f of x is equal to g of x for all points x in the complement of A. And indeed, there's a short way of saying that. You would write f is equal to g almost everywhere. And this attribute almost is to be seen with respect to the Lebesgue measure on Rn. Okay, and now our nice result we get here is that our new L-infinity space has a well-defined norm. So you could say it's a normed vector space, and actually it's also complete, which means it's a Banach space. However, showing this completeness needs some more work, and we should do this in the next video. So I really hope I meet you there again, and have a nice day. Bye bye.